Today we will talk about the second part of the assembly language. So I will explain each type of instructions. We have multiple types of them. The first one is, of course, the load and store. So there are two address formats. Base offset setting, addressing. Two address format. For the second arrival offset, and the base is actually stored in the R2 register. So the meaning of the first instruction, so data is stored in R2 plus 10, which is the address of that load. And the second instruction is to store the data of R1 to that address, which is R2 plus 10. This is we have memory. Memory is a section. 1 minute. Any register. Which is very through that address, by that address. The address, you can load some data from the address or store some data to the address. So the top part is C language. The bottom part is the assembly language. You can see that for 4 sentences in C language, we have to translate them into 6. So the meaning of this somebody 2 elements in that and add them together to store the result. Because we does not support directly manipulation on memories. You can only access memory by the load and the store instructions, which means that if you want to write, use the store instruction to store the data in that register back to the memory. This is called yes. Yeah, this is exactly what I'm going to start from a 0, 1, 2, 3. So you have 3 here. The 4. Right. So we are directly okay. For the base, for the items stored in the memory, they must be in a consecutive space. That because that's the definition of the list. So again, why we expand a lot of integer. So in the integer, in RISC, four byte, which means 32 bit. That's the reason why we have 4. By adding a 4, we can move from this side. But if you want to accept before that, any manipulation has to happen on the register level. You have to do the addition, subtraction, multiplication, or even move some data to the register, and then let the register to access the memory through only the load and store instruction. Yes.
Not quite sure how the basic.
Okay. So by so this file and so by doing a store operation, you didn't actually describe this file over in R1. And then you can directly do the addition by R1 and R2. So this is the branch. The branch instruction is unconditional different instructions. The label. Again, when you write CL, when you write C, when you write assembly language, try to avoid this instruction. If your application, if your code has a lot of these set, then you cannot manage them. You should use more. So the first sentence is if so typically these two before is some comparison operation. Then the result will be stored in. If they are the same, then the first one is 1. The second one is 0. If they are different, the first one is larger than the second one, then the second register, GT register will be 1 and the E register is 0. So this step to not swap, but store different values in the same register. The data in this register. E radical. This is but if R1 register. So by this sentence, you can assign different values to the same register, which is R3. So you can see that even a very simple loop in the C language will translate into so I have a comment. Yes. So I'm saying they represent the same way. In assembly language, they will be represented in the same way. So here is one example. This is a requirement. So besides I will explain that example later. So besides the instruction itself, we also have some so-called some modifiers. The modifiers can help an instruction to specify some immediate operand. So if you just write move and the sign. So which is done in C language if you declare a short. You assign -1 to this variable. And you declare another variable, which is a B. Do something like this. So if you want to keep this fine, then you need to use move. The move U can help you to treat the 16-bit immediate as an unassigned number. So if you use move U, you will get a wrong result. And we also have a move H, which left shifted the 16-bit immediate by 16 positions. Y left shift. So if you want to move 32-bit to some registers, you need to use move H for this 16-bit. So, for example, this is the register. If this register is a 32-bit, if you just use move or move U here, it will store the this 16-bit here. And then when you move another 16-bit here, it will move to the same position. That's not what you want. What you want is to use move H here and then move this part to the higher end of this register, higher end 16-bit here. And then use a move U to move this part. So you can see that at least for this tiny RISC simulator, it can only support 16-bit granularity memory access. but the CPU actually use 32 bit. So that's the reason why you need a different move instruction with different modifiers. So here is one example. If you use move, immediate data to R1 register. So this is the result. Each digit here is 16. Each 4B, not 16. If it's a half B, so 4B. So 2 4-bit data means 8 bit. 8 bit is 1 byte. So each bar is so move instruction treat this number as a signed number, which means that if the most significant is 1, then it's just 1. We keep it as 1. If it's a 0, then we keep it as a 0. Keep it as 1 or keep it as 0 means keep it 1, all 1. So the A is actually 10. A is a hex 10. This hex 10 is actually 4 bits equal to 1, 0, 1, 0. So the most significant bit here is 1. So if I treat this one as a signed bit, a signed number, all these should be 1s. But if you use move U, then you treat it as an unsigned number. Although the most significant bit 1, 2, 3, and if you use move H, then 4 is 5. So the lower end move another. So this is how you move this mobile. First, you use move H. Move the high end to R0 or to R0 register. And then you use addition. So the second half of the move is actually addition. And please notice that the open add U means you treat the two variables, two registers as the Einstein numbers. In the assembly language, we can also implement some functions. So that you can send different parameters to that function and get different results. Every function has a starting address in the memory. For example, this is one like A starting address. When we call a variable, we actually assign a value to the program counter. We actually assign the starting point address of that particular function to the PC, to the program counter. So before we assign that starting point address of that function to the PC, we need to store the backup the current address of the PC so that we can return this address to continue to run our code. And the current value of PC is actually the return address. We have a dedicated register to back up this return address. So the whole process is to call a function. Call a function means we assign the starting point address of a function to the PC. Before we do that, we need to back up the current value of PC. And then go to that function and then run the code of that function. After the function is done, restore the address, backup address to the PC. So the caller is in your main function, you can call any other function you write. So this is the current. And for that, we want to return so the return address is current address plus 4. Why 4? Why 4 bytes? Because nowadays we have 4 bytes. Each instruction is 30 bit. So you call the function here and then you have to use the function and then so for example, this is the call So how to pass some parameters or arguments to the function? You can use register. To get your data ready in those registers and then call the function. So if you want to pass a lot of parameters in the function, we only have a limited number of registers. Then you have to use memories. You have to first store your data in the parameter in the memory first, and then load those memory data back to the register in the function. So if a function calls itself, it's very common for sorting algorithm. Then the function may overwrite the register of the caller. The callee can overwrite the register of the caller, but all the functions share the same set of registers. You only have a limited 16, maybe let's say 16 registers. Then you have to store the current value of the register back to the main memory. So in order to make all the functions to share the same set of register, you need to frequently restore the current data of the register back to the memory. Because on these machines, they have unlimited space in the memory. So who will do the store operation? The store operation, store the current value of register back to the memory, can be done by caller or callee. So these are caller at the beginning of the function. They will save the register back to the and if this operation is done by caller, then at the beginning of the caller, it will save the registers. And at the end of the callee, it will restore the register. So from these schemes, we can see that the register is actually a very important resources on the CPU. If you have more register, you can reduce the restore operation to the main memory, which means that you access the slow main memory infrequently. But the point here is that you only have a limited number of registers. In this simulator, you only have 16 registers. On a real machine, you may have more, but again, they are limited. They have only a limited number. Why? Because each instruction is only 32 bits. You have to encode the name of the register in this I'm sorry, each instruction is a 32 bit. You have to encode the name of the register into this 32 bit. So assume that you use all 32 bit to index your register. There's no bit for the move, for the addition, for the subtraction, for the instruction. All the 32 bit, use the 32 bit to index your register. At the most, you can do these many registers. So the problem here is that even you have a very powerful CPU, which gives you unlimited registers, theoretically, you can only use these many bits to address them. So this is a real problem. But for the memory, because of the virtual memory, you know, virtual memory, physical memory, because of the virtual memory, you can assume that you have an unlimited memory space. Although you have a limited DRAM, physical memory, you can store your data even in the disk. So this is the memory organization. So we will keep a memory space for the parameter or arguments. You also have a return address. You also have the register store area. This is so-called stack. Because the size of these mapping of these, you can have one gigabyte, but you cannot declare 1 gigabyte. Here, give you some space for the local variables. If you want to have a very large array, you have to use the heap. This is stack, you have to use heap. And when you can do C, yes, C language or C++, you know the function of malloc free. Or in C++, you knew delete. Those sentences can help you manage a heap. So here is the algorithm. How to use the how to use the one activation. First, you need to do a lot of store, parameter, arguments, registers, return address, and then call the function. In the function, you also need to read the registers, save the return address, allocate space for the local variables, and then run the function. Once the function is done, you restore the values, particularly the value of return address register, and write the return address to the PC. And then call this return. Then go back to the call. Yes.
So are the registers always still, or is it only one?
Always.
Always.
Why? Because the color may have some data in the register. So even the color only use one register, the colleague may use the same register. So you have to do the backup first. And the so-called register backup the register or store the register. So all the information, arguments, return address, register values are stored in the activation block. So these blocks need to be dynamically. So how to guarantee they have a very fast speed? So we can see one example. In the main function, we call a test function. And then we call the second function. So you can see that there's a kind of first in, last out. But it lasts very long. The test 2 is the last function we have here, but it's first out. So this is the reason why we call it a stack. Last in, first out. We call the full function first. And the full so this is the reason why the activation block also called a stack. When you call a function, we allocate a piece of memory space for the stack. And the first stack starts at height. Because all the stacks are downward growing. So we can fix the highest address for the first stack. And then we have a stack pointer register to point to the beginning of an activation block. When we allocate because the original value at the beginning, the value of SP is the highest address. So we do subtraction. And we do addition when we destroy, deallocate an activation block. So by stack, we can solve the problem. What if we have a limited number of registers? Of course, we have a limited number of the space problem. We can overcome the overwrite problem. By the stack, we can also manage the multiple activation blocks. The stack is managed by the operating system. So when we call a function, we first back up the return address and then find starting point address of the function we call to the PC. At the end of the function, we would like to find the return. So this RET instruction actually help you to assign the address in RA back to the PC. So here is one example. So you recursively invoke. And then you can check this assembly language. You can try to run this piece of code in the simulator. So we call the function. So by the call instruction and the return instruction, you don't have to directly write any data to PC. Because the program counter is a very important register. Even the assembly language will not let you directly modify PC. You can only use jump, call, or RET, return instruction to indirectly modify PC. We also have a no operation instruction. So we actually decode the opcode by 5 bits. So these are all the instructions supported by the simulator. So the format of the instruction is defined as we have a file of opcode and the immediate data. So you can track this. So some instruction only have the opcode, like NOP or RET. They don't have any register or immediate data. So some instruction only have one address, which is a call B, BEQ, BGT. And then we also have the branch. And then we have a three address instructions. Shift logical operation and arithmetic operation are all these type of instructions. And we have a 16 register for them. So these operations can only happen on register level. So the operand has to be registered all from immediate data. So we only have a 16 register, which we need a 4 bit to address them. So this is the format. The first of these of code. And the code are for 3 registers. This ID, how many registers you need. So for example, if you have an immediate so the ID can help you distinguish these 2 types of instruction. Whether the operation happens between 2 registers or 1 register and 1 immediate data. So if you do have an immediate for the encoding of the immediate data. So if you have immediate data, you also need to specify whether it's a signed data or unsigned data or age. So in this way, we only leave 16. Immediate data, which means that you cannot have a super large immediate data. The immediate data has to be represented by 16 bits. And we only have a 2, we also have a 2 address instruction, compare, not, move. These are the formats of these 3 code. And this is the format of move, load and store. So when we encode load, offline. And the offset is, of course, an immediate data. So we need two registers. One is the destination, another one is for base. So this is a store instruction. It has two register sources, no register destination, and one immediate data. So the second operand can be either a register or an immediate data, but it cannot be both. And we don't need to define a new format. We can write the store instruction like this. So we use the RT to say one of the store. And then this space. So this is the summary of the instruction formats. The first example. The second one includes arithmetic operations, addition, multiplication, and the logic operation, and all. We encode the load store. The immediate format has one register and one immediate data. So in the previous slide, when we summarize the instructions, we didn't consider the modifier. Here, if you all the instructions, including the modifier. For example, for move, we call three types of move. We also call three types of subtraction. That's all. Thank you. Any question? So you can try to run the example code in the slide in the simulator, by the simulator. I also attach a lot of test cases, example code in the simulator. You can also run them. We don't have a class on this Wednesday because I leave that time slot for you to do your project. At least to read the example code and read the requirement and think about the project one. If you have any question, please go to the office hour on Friday and ask a question. Thank you very much.